Hi, and welcome to episode number 15 of CS350 Online. I'm your host, as always, Leslie, and in today's episode, we're going to continue our discussion of virtual memory for the kernel, specifically how does OS 161 implement it, and then we're going to take a look at our final topic of virtual memory, and that is on-demand paging, which is going to more closely represent how modern operating systems like macOS and Windows and any GNU Linux variation do their virtual memory implementations. But first, the OS of the day. So today's OS is of particular specialness, to me at least, and it's Sun OS, or Solaris as it became known in later days. This operating system was released in 1982, and it's a product of Sun Microsystems. Now, Sun Microsystems is a company that some of you might have heard of, maybe from me mentioning it, or maybe from hearing about it in CS251 or 241, but it doesn't exist anymore. And it might be easy to believe that Sun was just this tiny little backwater company, so who cares that it's not around anymore? Except it wasn't a tiny backwater company, and well, I'm kind of sad it's not around anymore, and I know there are many other people who share that sentiment. Now, a bit of that might be because I'm an ex-Sun employee, but actually it was a really nice place to work, and they produced many things that you use today. So Sun was an offshoot of Stanford, so Sun is actually not referenced like the sun, but Stanford University Networks, because one of the big things that their operating system and their hardware, because they were actually a hardware company as well, they were building on was really great networking support and really great networking architecture. So the first version of their operating system, which was known as Sun OS, was actually closed source distribution of Unix 7 and BSD. And closed source, so they don't share the source code to it. And what's interesting is in 83, Lucasfilm actually used Sun OS to be their operating system for their nonlinear editing system. So think of like a digital editing system, except, from like 35, almost 40 years ago. And they were exceptionally well known for having high quality graphics back in 83. Now, as someone who's worked there and I've used Sun products for many, many years, I can't really say in their later days they would be known for high quality graphics. I distinctly remember in 2003, is that when I worked there? Oh goodness, I don't even remember. So when I worked there, which would have been the early 2000s, the graphics interface, like the desktop environment, was worse than like Windows 3.1. It was bad. But, it didn't matter because you weren't using something like Sun for the purposes of the graphical environment. That's not what their operating system was really there for. All right. So, as I said, Sun did a lot of stuff with networking. I'm seeing a lot of network drops because of course I forgot to plug in my network card. Sorry about that. Please excuse this momentary interruption where I switch over from a wireless connection to a wired one. All right. So I imagine that's going to drop for a moment, and then have no fears, it will pick right back up as soon as it realizes there's a wired connection. Maybe. Or maybe not. So it seems There we go. For some reason, my wired connection isn't actually working today either. My apologies for the delay. It's not your end, it's my end on that one. But don't worry, once we upload to YouTube, there will be none of that craziness. All right, so other things about SunOS and Solaris. So one of the lovely, interesting things about Solaris is that, so in 1993, Sun actually became the first commercial 64-bit architecture on the market because they recognized at an early date that we were running out of 32-bit addresses. And if you had like a big data center, or if you were doing scientific computations, you were running out of addresses. So they realized they were going to have to up them. And they were the first to market, and that's the Spark architecture. And that's roughly around the time where they kind of started calling it Solaris instead of SunOS. Although I want to say even in the early 2000s, there was a lot of references to SunOS still. SunOS, Solaris, though, they're generally referring to the same breed of operating systems. So 64 bits was actually brought out by Sun. So if you have a 64-bit CPU, you can really thank Sun for being first to market with one. And as a result, Sun hardware and Sun software actually became exceptionally popular because they were the first with 64-bit addressing. So servers, databases, research labs, pretty much everybody had Sun hardware, and as a result, everybody was running Solaris as an operating system. And I can tell you that when I joined Waterloo in my undergrad in 2001, we were using all Sun products. So we didn't have a GNU Linux distribution. We didn't have just generic hardware servers. Waterloo's math students got access to the Sun servers, and that was it. We didn't even get access to the Windows labs unless we were taking like an arts course. They kind of kept math computing environment quite segregated from the other departments of the school. And then it wasn't until many, many years later that they decommissioned the Sun machines. Of course, Sun also went out of business. Now, if you're wondering, I said this was a really big company. How big? Well, it was as big as Microsoft, as big as Intel, as big as IBM. It was one of the big ones. And what killed them was people started to realize that you could go down to your neighborhood Canada Computers or NCIX or Fry's, whatever computer store you have, and you could buy for very little money enough computing hardware to build yourself your own little cluster. And that cluster would be a fraction of the price of the Sun hardware, and it would be quite possibly faster than Sun's hardware. And since it was just a bunch of commercially supported hardware, you could run whatever operating system on it you want. There was no requirement to purchase a specific OS. You could just download some GNU Linux distribution and use it, and it would work. So it was cheaper to purchase the hardware. It was cheaper to maintain, because if a part broke down, you could just go buy another one for $100 instead of having to pay for Sun to actually come and repair it for you. And as for an operating system, well, you could get free ones, like legally free ones. And this started to cut into Sun's market as more and more companies started to investigate this. And Sun kind of caught on a bit too late. Now, when I was there in 2003, as I think it was, they were starting to experiment. Like, I was running some clustering experiments. And they weren't taking it terribly seriously, at least at our office. And eventually what happened, so when I was there as a co-op student, they did 10,000 layoffs, and my office was actually decimated by this. We went from having, a very full office to, I want to say, 80 to 90% of our full-timers were laid off. It was actually quite crazy. Now, they didn't lay the co-ops off, of course, because co-ops were relatively cheap, and we were going to be gone anyways in a few months. But it was it was a bit scary of an experience to be around a massive layoff like that. But it was also in some ways very interesting because they started to realize that the jobs that the full-timers were doing was very necessary. And so they needed the co-op students to now take over for all the laid-off full-timers. So if you want to know where a lot of my operating system experience actually comes from, it comes from Sun actually paying to train me in these topics so that I could take over for the laid-off full-timers. So there you go. Fun story. Sun ended up, or at least the remnants of Sun got purchased by Oracle, which isn't a huge surprise. You can actually still get the Solaris operating system. I'm not sure how well maintained it still is. Spark processors are sort of still being made, but not really being used except in super high-end things and people who are super loyal. Another fun story, the reason why I ended up getting a job at Google much later on was actually because I had worked at Sun this exact same time that my boss at Google had worked at Sun, and we had both gone through those layoffs. Sun loyalty. All right, enough of the fun stories. So, let's go back to where we were. So in our last episode, we were talking about multi-level paging. So we finished off with some examples of multi-level paging, and I really recommend that you get some experience with the math. And in particular, I highly recommend that you go on Piazza, and there is a virtual memory guide. See if it opens up here. Blah, blah, blah. I don't care about the cookies. Is this terms? Yes, must be this terms. So if you go into... Oh no, it's become unpinned. How did that happen? Oh, here it is. Extra sample problems and lecture content. So if you go into here, you'll see there's a bunch of extra content, stuff like a virtual memory guide. My recommendation to you is to get some experience working with the different address calculations, and this guide will help you with that. The kinds of things that you'll see in this guide is actually an overview of the different formulas, and then for each of the formulas, there's actually going to be 1 or 2 examples of using those formulas. So we've got everything from computing the number of bits for the page number to computing the number of levels and so on and so forth. So there's this guide here, and if you're struggling with those topics, please make sure that you check that out. Then we started talking about the concept of a TLB. So one of the problems with something like paging, especially multi-level paging, is the fact that for every address translation, you actually have to go to RAM to grab the page table entry, which of course is going to pose as a bit of a delay, because if each instruction requires at least 1 memory access, that's a lot of memory accesses. So even for single level paging, it became incredibly useful to actually have a TLB. It's an onboard cache where we can store page table entries. And then for multi-level paging, which instead of requiring 1 memory access, could require 3 or 4 memory accesses per instruction, this became increasingly important to actually have a TLB. There were 2 kinds of TLBs. There was the hardware managed, which means that the hardware handles the lookup from the page table when there's a cache miss, and it also means that the hardware is dictating the format of the page table entries. So it's faster, but it's producing restrictions to the user. And then the software managed TLB on a TLB miss, as a cache miss, it's going to throw an exception and have the kernel handle the exception. Now that's not going to be as fast. However, because the kernel is responsible for updating the MMU and the TLB, then we actually have a lot more flexibility in how we actually implement our paging in the operating system's kernel. So most operating systems choose to do a software managed, and most hardware architectures use a software managed TLB. Then we started talking about OS 161's implementation. So we showed you the format of the TLB entries in a MIPS R3000, and we started talking about the virtual memory space for OS 161 and how even though our MMU is paged, we're technically doing segmentation. And how we have managed to merge those two things together is by noting that if you just have the allocation of pages for a segment be contiguous in physical memory, then you're effectively allocating different sized regions. So you would have 7 contiguous pages be allocated in physical memory, and that would be a different size than the 5 contiguous pages you needed for the data segment. Now, on the last class, we also showed you how to perform the segment address translations. And this little bit of code here is something you're going to get a lot more familiar with when you get to assignment 3, because you're going to be making a lot of modifications to the function that contains this bit of code, and that is vmfault, which you will find in dumbvm.c. Then we practiced some address translations for process 1, and again, you're welcome to try process 2 on your own. And then we talked about, finally, where does the address space actually get this layout? And that's where I want to continue things from today. So, at the end of the last class, I introduced the concept that all of the information for the address space's layout was actually stored in the binary file itself. Which kind of makes sense because your compiler knows how big the code segment is, and your compiler knows how much global data you have. And so it makes sense that the compiler would know how big those segments actually need to be. And so your compiler is indeed going to put that information into the header of the binary format. Now, our binary format is called ELF, Executable and Linking Format. It's very similar to 241's format. And if we look inside, we're going to see lots of different things. Now, I tried to give you a demo last class, and it wasn't working. I've got it working today. I promised that I would. So what we're going to do is we're going to run this function called CS350 object dump, which is just the 350 variation of object dump. And we're going to take a look at the header information for test bin sort. All right. So there we go. Let's try to make this so everybody can see. So what you can see here in our header is all of the different segments for that the binary file is telling us about. So the header will tell us. So the first one is this text segment. The text segment is actually the code segment. And what you can see in this file is it tells us how big the segment should be. It tells us where the segment should live in virtual memory. And it tells us where in this binary file can we find that segment. So that's pretty cool. And then underneath, it tells us a bunch of information about what we should do with this segment. Now, a lot of these things aren't really that interesting to us, but you will notice that this segment is marked as read-only, which means when we load this segment into the address space, it should be treated as read-only, which means that when the user tries to write to this after the initial load, they shouldn't be allowed to. Now, immediately below that, you'll see there are 2 other read-only segments. The next read-only segment is the read-only data. That's actually the constants. And the constants, as you'll see, again, we have the size and the location in the file. That's actually going to be combined in with the code segment in OS 161. So we're going to put those 2 together. And then the next segment we care about, we don't care about all these other things down here. The next segment we care about is number 3 in the list, data. And there's the size of the data segment. Then remember, that's our globals. And there's the address where it's going to live. There's where it is in this file. And you'll notice that the read-only comment is missing because this should be read and write. So all of this information about the code in the data segment is actually found right in the binary file. But what is suspiciously missing is the stack. Well, let's think about this rationally for a minute. If you're a compiler, how do you know how big you should make the stack for the program? Can you make any estimations? And I know the answer to that is yes. But how accurate are you really going to be? because the usage of a program kind of depends on how a user, what they're doing with it. So in a lot of ways, it doesn't really make sense for the compiler to try to estimate a stack size. Not to say that it can't. In reality, we actually let the operating system determine the stack size. And so since the address, what was I talking about? I've forgotten already. So since the operating system actually determines the size of the stack, there's no reason for it to exist in the binary file itself. Now in OS 161, your stack is 12 pages, so 48 kilobytes. And in something like Windows or Mac OS or any version of the Linux kernel, you typically see a stack size of about a megabyte, maybe 2 megabytes. Not terribly big, but there are system calls that can actually expand upon it. Now, a question on Twitch here. What's the difference between VMA and LMA? Actually, I'm not 100% certain. I believe, so VMA is where in the address space, the virtual address space, the segment begins. And LMA, I believe, is where should I start loading the data into that segment. Now, and I mean, that makes sense. But you might be wondering, why do we have to specify the VMA and LMA separately? Because in some operating systems, even if the segment starts at 400,000, we may actually put some padding and load the segment in somewhere else, or load the actual data into the segment at a slightly different position to permit linked things to be added and so on. So it really comes down to some architectural implementations. All right, so let's go back to our slides here. Now, we've talked about why we don't describe the stack, and then at the very end of the day, we started talking, last class, we started talking about virtual memory for the kernel. Now, we want the kernel to live in virtual memory because abstraction is a good thing, and because we want to be able, the kernel to maybe be able to take advantage of things like on-demand paging, but this actually runs us into two really big problems. The first of those problems is bootstrapping. So if the kernel is what implements the virtual memory, then how does the kernel run in virtual memory while the operating system is booting? So that's a problem, and it's actually typically solved architecturally. In OS 161, you'll see that we're effectively using a hard-coded address translation, which is kind of fun. But I mean, it works, and it solves the bootstrapping problem. Then we have the sharing problem. Now, the sharing problem is if the kernel and all of the processes, if their address ranges are all the same, how can you copy then from one address space to another? Because you only ever read or write virtual addresses. And this is really, really important in this course, especially when it comes to A3. You cannot read or write a physical address because your MMU translates every address. So if you try to read or write to a physical address directly, your MMU is going to translate that address that you thought you were writing to into garbage. So you can only ever read or write virtual addresses. So how then, if every process is and the kernel are using the same range of addresses, how do I know that this is address deadbeef in process 1 and not deadbeef in the kernel? So we don't really have a way to effectively copy data between these things. And the sharing problem is actually really easily solved. And that is to restrict further the size of virtual memory and then say these addresses are reserved for the user and this different range of addresses are reserved for the kernel's virtual addresses. And that split is 50-50. It doesn't have to be 50-50, and certainly other operating systems have done different splits, but 50-50 split is the most common one. And the lower 50% of addresses will be for the user process, and the upper 50% of addresses will be for the kernel processes. And what's interesting is now we can differentiate. This is a user address, and this is a kernel address. You ever wonder why I know based on EPC where your program's error comes from? It's because of this 50-50 split. I know where it came from. So this is something, by the way, even Mac OS and Windows and the Linux kernel do. And if you don't believe me, it's actually really easy to test this out. Start writing to the stack. Try to fill up virtual memory and see if you get any addresses beyond the 50% point. And you don't. And you can't. So the interesting thing now is that because the virtual addresses for the user process and the virtual addresses from the kernel no longer overlap, it becomes easier to share data because we can take data from the user process, put it into the kernel, and then from the kernel back into a user process. So that's kind of neat. Now, this also, in a way, really helps the MMU, because if the MMU is aware of this split, and in a lot of cases the MMU is aware of this split, this is part of the bootstrapping architectural implementation. Now that the hardware is aware there's a 50-50 split, if you are in user mode and you try to read or write from a kernel address, the MMU will throw an exception. Because you can't do that because you're in user mode, and it recognizes that kernel address as being a privileged address, and you are not currently privileged, and therefore you're not allowed to access it. So that's kind of a neat thing. So let's look a little bit more closely at how OS 161's memory is actually set up. So as you know, we have 32 bits for virtual and physical addresses. Question on Twitch here. So we can use that 50-50 split to ensure we're copying stuff correctly into the kernel for A to B. Yeah, I mean, so you're going to be using things like copy in and copy instar to correctly copy from the address space of the process into the kernel. But then if you look at the addresses in the kernel, you should see that they're actually like kernel addresses. And if they're not, then you've done something kind of messed up. But we'll talk more about how we do that kind of stuff another time. Well, I guess we've already talked about A2B, haven't we? So yeah, you can actually use that a bit to diagnose things. But really knowing that 50-50 split, that's important for fixing those TLB misses. As is this diagram here. So 32 bits for physical, 32 bits for virtual memory, so we have 4 gigabytes each. However, the simulator that we are using actually only supports a gig of RAM, so anything beyond this address here is just not supported at all. Then if we look at how the virtual memory is divided for OS 161, we have a 50-50 split, again the most common split, and the lower 50% is the user. The user's memory is at a hardware level paged, as the physical memory is as well. And then the kernel addresses, which occupy the upper 50% of the virtual addresses, are actually further divided into 3 separate segments. So kseg0 is probably the most important segment you should know about. kseg0 is actually the kernel's memory. So that is where the kernel's heap is, that's where the kernel's code is, that's where the kernel's stacks are. All of the kernel's data, all of the kernel's data structures lives in kseg0 addresses. Okay, and then we have kseg1. And kseg1, these addresses aren't actually really used. In fact, the majority of this space here is unused. But if you have an address from kseg1, it means you're trying to talk to a piece of hardware. And I know right now we haven't talked about how to interface with hardware, but we will be shortly. Because in episode number 16, we'll be talking about scheduling. Scheduling takes about 1 episode, maybe a little bit more. And then in either episode 17 or 18, we'll be starting to talk about devices. And this segment will make a lot more sense then. And then finally, we have kseg2. And kseg2 is actually unused. It's unsupported. And this is not actually an OS 161 thing. This is actually a MIPS R3000 thing. So I was reading through the R3000 spec a couple years ago, and kseg2, yeah, that's not actually supported. Now you might be thinking to yourself, but that's a gig of memory that we are just not using, and isn't that a big deal? But you have to keep in mind what years this processor was actually used. This was the main processor for the PlayStation 1. This was a secondary processor for a PlayStation 2. So not the main one. It was like a co-processor on the PlayStation 2. But it was the main processor for a PlayStation 1. So when did the PlayStation 1 came out? Like, I don't even remember. Late 90s? Mid-90s? Things weren't that big back then. So even though this segment wasn't used, it wasn't really a big deal. Now, there's something else that we introduce at the bottom of this slide, but we don't really talk about anywhere in the virtual memory slides. But we will talk a lot more about when we talk about how to do A3, and that is the concept of a core map. So how do you keep track of all of this physical memory that we actually have? Because if I want to do some kind of allocation for these pages, I need to keep track of which frames of physical memory are actually available. So what we have is this structure called a core map, and it lives in the kernel. And the goal of the core map is to keep track of all of the pages of physical memory that are in use and that are free. And the idea is whenever you request a page, you ask the core map to give you a page. And whenever you free a page, you tell the core map to free it. OS 161 right now doesn't have a core map. You need to implement that for A3. But we'll talk more about it another day. Now, the user addresses, which are paged, are actually going to be cached as well. So what we mean by that is we are going to be using the TLB to perform the translations for the user addresses. The user addresses can technically be mapped to anywhere in that 1 gigabyte, but they don't typically be mapped to the early addresses down here, the lowest addresses, because something else is going to live there instead. Now, you've already seen how the address translations for this work, so we're not going to go over that in any more detail. But what about these kernel segments, kseg0 and kseg1? So these are actually translated very simply. They are not paged and they are not cached. What we do instead is kseg0, we are going to go from virtual to physical by subtracting the offset. And the offset, of course, is this value right here. And that will take you from virtual to physical, which means that kseg0 technically maps to the first 512 megabytes of physical memory. Now, you might be wondering, does that mean that I only have 512 megabytes left for the user addresses? No, actually it doesn't. So we're saying, when we say that kseg0 maps to the first 512 megabytes of physical memory, we are not saying that we have set aside 512 megabytes for kseg0 in physical memory. We are saying kseg0 can use up to that 512 megabytes, but it doesn't have to. So for example, OS 161 obviously doesn't use 512 megabytes of RAM, which means it might use a couple megs of RAM. So that first few pages might be set aside for the kernel's memory, but then the user processes can use any pages beyond that. And in fact, that is actually when you will see when you implement A3, that's exactly what is happening. Then kseg1, again, not paged, not cached. To translate from virtual to physical, we are going to again subtract the offset, which means we are subtracting this number right here, which is somewhat covered up. And I guess it's down here as well. But this means that kseg1 actually overlaps with kseg0 in physical memory because they both map to the first 512 megabytes of physical memory. So what the hell is going on here? Does that mean that kseg1 is going to trample all over kseg0? No. So kseg0 is the actual kernel memory. That's where we would put it. But remember, we're probably not using all of it. And kseg1 I said was going to be using for addressing devices. Now this is a part of the architectural specifications, which means that the operating systems are very much aware of this. And so the kernel knows that whatever kseg1 addresses we need to use cannot be used by kseg0. And in fact, as we will see, very few kseg1 addresses are actually used. such that the OS 161 kernel would never use those addresses anyway. So we're prevented from doing that. So even though those ranges technically overlap, when we are implementing the operating system, we will make sure that data doesn't get clobbered and it works out. We're not going to use all of KSEG1 because KSEG1 is simply to identify I'm trying to talk to a device. And there aren't that many devices and there aren't that many things we need to do with those addresses. So we only need to use a teeny tiny few of them. And again, this will make more sense at a later date. So if you have a physical address that falls in the first 512 megabytes, then what you have is, if you had to choose what virtual address could have resulted in translating to that physical address, there are three choices. So in the first 512 megabytes, it could have been a user address, it could be a KSEG0 address, and it could be a KSEG1 address. So that's a kind of a fun thing to do. And again, just to keep in mind, KSEG2 is not used. Now I want to take a brief intermission to look at a problem. So if you are on the core Piazza, you'll find one called MIPS Translate. And MIPS Translate, I'm only going to do 2 of these with you, the first 2. And I'm going to let you do the other 2 on your own. So let's get a new page here. And after we've got a new page, let's give us some lines. Probably should have plugged my tablet in at an earlier time. All right, so what we've got here is we've got, instead of a bunch of virtual addresses we want to change, we have a bunch of physical addresses, and we want to know, given that this is OS 161 and SYS 161, what are all of the possible virtual addresses that could have translated to this, or virtual address that could have translated to this physical one? So we're not saying which one did. I'm asking you, what are all of the possibilities that could translate to this physical address? So let's look at the first one here. So we have, oh, lovely red, 1113 FA0. So the first question you should ask yourself is this in the first 512 megabytes of the address of the physical memory or not? And it is. It is in the first 512 megabytes. So that means that I know off the top that a KSEG0 address could translate to this, and a KSEG1. That's some good spelling, isn't it? And so to get those, I am going to, instead of subtracting, now I'm going to add. So I am going to get so there's my KSEG1 address, and there's my KSEG2 address, or KSEG0 and KSEG1. Yay. The next question becomes, is there a user address that could have also translated to this? And we've got a page table here. We're going to do a reverse lookup. So instead of looking up the page number, we're actually going to look up the frame number. So our frame number here is 01113. And if I look up that frame, I actually find it, which means that we could also have come from the following user address. So all 3 of those virtual addresses could translate to this physical one. Remember, we're not asking which one did, we're saying what are all of the possibilities. Now, let's do one more, and then I'll let you do the other 2 on your own. It's important to get practice, right? So now we have, and again, you'll notice I'm dropping the leading zeros because I want to, but they're still there. So again, I note that this address falls in the first 512 megabytes, so I know that there is a KSEG0 and a kseg1 address. And so I'm going to write those ones out. So we have, again, we're adding our offset instead of subtracting because we're going the opposite direction. So there's my kseg0 and there's my kseg1 address. And now I'm going to look it up in the page table by looking up the frame number. So my frame number is 0100A. And I looked that up and I do find it. So I'm going to get 004088. So there you go. That's going backwards. All right. So that's kind of the end of talking about the kernel's virtual memory. And there's one final topic to talk about in virtual memory, and it's my favorite one. Sometimes I swear everything's my favorite. But there you go. So one of the problems that we have with the virtual memory implementations that we've shown you so far is that they're kind of restrictive to how much memory you can use. So, for example, what I mean is that if there isn't enough space in physical memory for that segment or there's no more pages left, you can't actually do anything. You can't load the process. So that's a problem. But if you think about how many processes you have running today, and we can look that up real quick. I'm going to guess and say for me it's over 250. Let's see what I got. Today I have 506 processes running. I think I technically have a Chrome tab that's or Chrome window open that's probably got like 15 tabs in it because that's kind of my version of I'm doing all these things right now and I don't want to forget. Also like 3 different Slacks so I can keep track of all my different groups I'm a part of. Lots of processes. But if you think about how much memory each of those processes, so 500 processes. 500 processes. Okay. Now, this Mac here technically has 32 gigs of RAM, which isn't a lot. I wish it had like 128 gigs of RAM, but, you know. Apple doesn't let you have that much RAM. At least when this machine was purchased, it didn't have that much. So 32 gigs of RAM and 500 processes. So that really means that each of my processes aren't getting that much memory. So, I mean, we could actually calculate it out here. Let's see if we've got, 32 gigs. Where'd that calculator go? Why does it start over on the other screen? It's very strange for the record. If I seem to be struggling to drag Windows from my other screen to my main desktop, which is actually shared, it's because the external monitor I have is a much, much higher resolution than the MacBook Retina screen. Okay, so we've got 32 gigs, and let's divide that by my 503 processes. So that means that each of my processes can use 0.06 gigs of memory. That's not a lot, really. That's like not much at all. And especially if you're using like programs like MATLAB, which has like a huge memory footprint. I use OBS to actually do the streaming here. That's got a pretty big memory footprint. Chrome uses like gigs and gigs of RAM. So how is it then that I'm able to have so many processes running with so many memory demanding ones at that, and yet only have 32 gigs of RAM? It's because they do something called on-demand paging, which is this greater concept of exploiting secondary storage. So what's going to happen is instead of keeping the address space in RAM all the time, we're actually only going to keep a fraction of the address space in RAM that pertains to the exact piece of the address space I'm using right now. and the rest of the address space can live somewhere else, such that my footprint in physical memory is really, really small. And if I'm not actively running right now, then why am I in RAM at all? There's no reason to be. Which means that I have a lot more physical memory to run other things. So this concept of letting the address spaces, the parts of the address space live elsewhere other than physical memory that you're not using, is actually really helpful to letting us run more processes than we technically have memory to support, or a singular process which needs more memory than we can support. Now, another way to think about this is to actually think about things like MATLAB. So I don't know how much you've used MATLAB. I don't know if you've taken CS350, and I don't even know if they still use MATLAB in that course. MATLAB and I go way back. Another day, another time, many, many years ago. You want to know why I seem to be quite comfortable with MIPS? It's because once upon a time, I actually wrote a MATLAB compiler and optimizer for a vector-based MIPS CPU. So if you're wondering what vector-based MIPS is, it means that instead of each register being a singular integer, each register is actually 8 32-bit integers. And the MIPS instructions, which are actually like the same, or very similar to the ones you're familiar with, they can, instead of doing like add one int to one int, you could actually add 2 whole vectors at a time, which is really cool. Yeah. Anyways, MATLAB. If you were to actually install MATLAB on your computer, it's huge. It's absolutely massive. And I'm going to guess and say that you don't know what 99% of the stuff is that's in MATLAB. For example, did you know that you can take your MATLAB program and it actually has something built in to translate it into a C program for you? That's pretty cool, right? But you didn't know it was there. And there's things like the Simulink Lab. There's all kinds of crazy stuff that you can do in MATLAB. It's a very, very complex and sophisticated tool. But if you're sitting down and all you want to do is multiply 2 matrices by each other, or compute the inverse of a 4x4 matrix, then all of those gigs and gigs and gigs of program code you're not using. So what's the point of loading it if you're never going to use it? Another way of thinking about this is if you look at an operating system's code base, like the actual kernel, looking at the Linux kernel, looking at the Windows kernel, now they are billions of lines of code. And you might be thinking, wow, how is the kernel, which is like virtual memory process, how is that billions of lines? Really? But it's not. The actual code that comprises the virtual memory system and the file systems and all of the kernel functionality is actually not that big. But all of those other hundreds of millions of lines of code that exist in the kernel of Linux or in Windows actually correspond to device drivers that are built in. And they have device drivers for every crazy device you can imagine. So for example, Dvorak keyboards. And I'm not sure if you've ever heard of a Dvorak keyboard before. You're familiar with the QWERTY layout because the QWERTY layout won. But my understanding is the Dvorak layout is actually more ergonomic than QWERTY. When I was a kid, I actually had a Dvorak driver, and I didn't know what it was. I thought it was a game, and so I kept accidentally, like the one day I started up the Dvorak program thinking, oh, I wonder what this cool game is, and it screwed my keyboard layout. So that's how I discovered Dvorak. But you have Dvorak drivers in your operating system. You have sound card drivers for Sound Blaster 16s, which haven't been in use since like the early 90s. You have drivers so let's suppose you're using some version of GNU Linux. You have a driver in your operating system for 9-pin printers. Now, I don't know if you know what a 9-pin printer is. Once upon a time, I used to write drivers for them for the Linux kernel. But it's a printer that actually has a physically moving part that hits, kind of like a typewriter. There's a little hammer that has a ribbon with ink on it, and the hammer hits the ribbon and smashes the ink-filled ribbon into your paper. And they're noisy and awesome, and people technically still use them for some reasons. But your computer has a driver for that. Do you want these obscure device drivers taking memory away from your processes? Of course you don't. And so exploiting secondary storage lets us keep all of those parts of the address space, all of that program code on disk, and instead of being loaded into memory. So we're only loading the parts of the address space we actually are using. So How does this actually work? So we're going to need to add some bits to our page table entries. So first off, we're going to add a bit called the present bit. What the present bit indicates is this page in physical memory or not? And then the set of all virtual pages that are actually present, that is, they have their present bit set to 1, we call that the resident set of the process. What is actually in memory right now is the resident set. So we have this bit to indicate whether you are in memory or not. If you are in memory, then your page table entry should be valid, and you will have a frame that you are associated with. If your present bit is 0, it doesn't mean that the page table entry is invalid. It just means that you are not currently in physical memory right now, which means the frame number in the page table entry doesn't exist. And it doesn't exist because you're not in memory right now. And then if the valid bit is 0, we honestly don't care what the present bit is because it's not a valid page. Okay. So how is this going to work? So what's going to happen is that your TLB really shouldn't contain any entries in it whose present bit is 0. Now this actually makes perfect sense because if you think about a TLB, it's supposed to contain things that are actually in memory right now and relevant. So it's like we don't keep page table entries in the TLB that correspond to invalid pages because that makes no sense. That's wasting space. And if the TLB contained an entry where the present bit was 0, then we'd have a problem because we wouldn't, even though the TLB contains that page table entry, the page table entry doesn't work out because there's no frame. So we can't actually perform the translation. Now, there's 2 ways that you could do this. The TLB could contain such entries, and when it checks the present bit, it throws an exception. Or you could simply have the kernel manage the TLB to make sure that the TLB never contains anything that isn't present. And that's totally doable because what's going to happen is we're actually going to detect our page faults, which means that the page is not in physical memory, on a TLB miss. So we're going to say that our TLB only contains things that are present. So when we do a lookup in the TLB and we don't find it, we throw an exception. And then inside of the kernel, we're going to look at the present bit for that fault address. And if the fault address, we notice that its present bit is 0, then this wasn't just a TLB miss, this was actually a page fault. And what we have to do on a page fault is the kernel has to look up the page in off disk. It's going to have to load it. It's got to find a place in physical memory to put it. It's going to load it in. And then it's going to update the page table entry because now we are present. Now we have a frame number. We're going to add it to the TLB now, and then we'll return from the exception, and the address will retry, and it will succeed. But there's a few details. What if there's no physical memory free in order to put that page you want to load? Well, we're actually going to have to start treating RAM as a cache, and we're going to have to start evicting pages from RAM to make sure that there's space. And when we evict something from RAM, we've got to make sure that we update our TLB to indicate, oops, this isn't here anymore. All right. Now, what that means is that every time we have a TLB miss, we could actually have a page fault. And a page fault is actually very expensive because page faults are going to require not just reading from RAM, which is more expensive than reading from the TLB, but a page fault has to read from secondary storage. And if you think going to RAM is slow, it's got nothing on secondary storage. It's secondary storage, like a hard drive or an SSD, is orders of magnitude slower than going to RAM. And if you want to know kind of the impact it would have, so let's suppose that accessing secondary storage is 1,000 times slower than RAM. That's a very reasonable assumption. So if you have a page fault, a true page fault, for every 1 for every 10 memory accesses, so that's not even like 10 assembly instructions. That might be as few as 5 assembly instructions. Then your program is going to be 100 times slower due to page faults. 100 times. So my program that was supposed to take 1 second now takes 100 seconds. And I don't know about you, but if I have a program that's supposed to be almost instantaneous and it takes over a minute and a half, I'm going to throw my computer out the window, which may be not an inappropriate reaction, but I think you get the point. If we have one page fault for every 100 instructions, or not instructions, memory accesses, then our program is 10 times slower. 1 in every 1,000, now we're only 2 times. And for 1 microsecond to 2 microseconds, I can handle that. That's okay. The point that we're trying to make here is that on-demand paging had some really great advantages. In particular, because we now only have to store part of the address space in physical memory, we can have really large programs run. We can have hundreds of really large programs run, and it seemingly all works out, even though we don't have enough RAM to technically do it. Unfortunately, we get a significant amount of latencies when we get the page faults. Now, there's lots of different ways that you can solve the page faults. One of the ways that you can do that is to just limit the number of processes that are allowed to run so that there will always be enough physical memory for every process. That works. Technically, that works. But that's going to restrict me to like 10 processes. And I don't know about you, but I don't think I could live in that world. I mean, technically speaking, I did grow up in that world. My first computer didn't even have a hard drive. So everything was self-booting, and you put the disk in and then you turned the computer on. There was no hard drive. So yeah, only one process, obviously. But today's world, 10 processes? No, I don't think so. Another thing that you can do is to be smart about which pages you're keeping in physical memory to try to reduce the number of page faults. And that's actually where we're going to spend the rest of our time. But one of the other strategies that you could use, and some architectures are actually doing this is to hide the latencies and prefetch the pages before you need them. Now, actually, we talked about Sun earlier today, and now we can actually talk about Sun again. How exciting. So here's the thing. Sun's Spark architecture kind of still lives on, and it's still kind of being developed. They have a 32-core architecture, and what's interesting about this is that instead of having all of the cores be just general use, they've actually reserved 2 cores to be for kernel operations. And what that means is they can actually utilize one of the cores just to do page prefetching. So you can predict, based on the address translations that you've been doing, what pages you're going to need next. And then you can prefetch using a dedicated core in parallel that page so that the faults don't happen nearly as often. We're not going to really talk about that because that's architecturally specific. Your consumer processors might do a little bit of that. I don't really read their specs that clearly, but it's not that interesting. What we want to talk about is just being smart. So we need a page replacement policy, which is also known as a cache eviction strategy, which, by the way, is still one of those active research areas. So first in, first out is the obvious answer, because we always want to be using the keeping things in memory that we've used most recently. Okay, first in, first out. That makes perfect sense. So let's look at this example here. Here's a bunch of numbered memory accesses, and the letter is going to be the page on which that access occurs. Now, we've really restricted our memory here to RAM has just 3 frames, but it's to show you the example here. So when you start off and you load the process, you're not going to load the address space. You're not actually going to start loading pages of the address space until you actually start executing. So the first time you need to access something on page A isn't in memory, so it's a page fault. That's what these X's are down here. So we load it into frame 1. We don't have to perform any evictions because there's space. Same with B, same with C. But it's when we get to memory access number 4 and we want to access page D where we start to notice that, hey, memory is full, I need to choose somebody to evict. First in, first out, I evict the oldest page. So I evict A. Oops. while that was very simple to implement, and while that makes a lot of logical sense, the problem is that we ended up using A again in the very next instruction. So we just evicted A, and now we're going to use A. So we evicted the next oldest one, which is B, and then of course in memory operation number 6, then we need B. So first in, first out, easy to implement, doesn't really reduce our page faults. What does? Well, we know what the optimal page replacement algorithm is called. It's called min. We are going to replace the page that will not be used for the longest period of time. So when I come to memory operation 4 here, I've got to choose between A, B, and C to evict. And I look ahead and I see, oh, I immediately use A again, and I immediately use B, but I don't use C for like 6 more operations. So C is the safest one to evict. So I'm going to evict C. No page hit, page fault. And again, I see A and B are really used really quickly, so I'm going to evict the from D, hit, miss. So you'll see here we have fewer misses. Now, you might be wondering, why do we still have 4 slides left in this module? Is it all review? We have our optimal algorithm, so what's wrong with it? It requires knowledge of the future. Sorry, I was getting a little overexcited there. So this we know would be optimal, except it's also impossible because we don't know the future. I don't know what memory access I'm going to do 20 instructions from now, because we don't do that much look ahead. I mean, you can do a little bit of look ahead, but I don't know what my user's going to do. I don't know if my user's going to push the different buttons on this device, and I don't know what reactions are going to happen. So we can't implement this. It's impossible. But we can estimate it. We can make some predictions using this concept of locality, which we've kind of talked about before. So there's 2 kinds of locality. There's temporal locality and spatial locality. Temporal locality means that if a process is using certain pages, they're probably really likely to use them again in the near future. So if I'm using page 17 right now, then I'm probably going to use page 17 in the future. And the other one is spatial locality. So if I'm on page 16, then I probably am going to use page 15 or 17 in the near future because they are spatially located where I am right now. Now, why does that make sense? Well, if you look at, let's bring up one note here. Scroll down. If you look at like just a list of instructions, so we've got this list of instructions. What are the addresses of these instructions? Well, this would be, address, let's say 0. This is address, 4, address 8, address C, and so on and so forth. So these are sequential instructions. And what that means is that if this is on page 0, then this is probably on page 0. And this is probably on page 0. So both temporally and spatially, I'm going to use page 0 in the future. So can we take advantage of locality to predict which pages we're going to use in the near future? Of course, that gives us the least recently used page replacement, which means we're going to choose the least recently used page to be the one that we evict. Now, this example in the notes is particularly bad because this makes LRU as bad as FIFO. We're not saying that LRU is universally better than FIFO, but we are saying on average LRU is better than FIFO. So, again, when we get to memory operation 4, we're not going to choose the oldest. We're going to choose the least recently used, which in this case is also the oldest, which is A. And that's where the problem with this particular example comes in. However, that you can't implement either. Here's why. To implement LRU, we need to keep track of every single memory access. So every time I do a translation, I need to keep track that I did a translation on that page. Now, but the problem is we don't actually do this. We could, now the kernel could keep track of it, but the kernel doesn't know about every successful address translation. So since the kernel doesn't know about every successful address translation, it only knows about the ones that weren't successful. We don't actually have a way to keep track of who was recently used and who was least recently used. So that doesn't really work. Now we could get the MMU to help. There's a few different ways that we could do this. We could have the MMU actually keep timestamps, but timestamps are going to be particularly costly, so we don't want to do that. So what we're going to do instead of doing timestamps, which would require, a very big register, we're actually going to have a single bit called the use bit. And that's going to be stored in the page table entry. And the idea is that every time the MMU uses a page for a translation, it is going to set the use bit to 1. That's it. Just set it to 1. And then what's going to happen is periodically the kernel is going to clear the use bits. So instead of knowing who was least recently used, we're going to know who was used since the last time the kernel cleared. So it's not as accurate as keeping a timestamp, but in terms of hardware cost and in terms of implementation costs, it's going to be cheaper. So let's look at an implementation that makes use of the use bit. This is called the clock replacement algorithm, and instead of showing you this with this slide, I am actually going to show it to you in OneNote. And again, just as a quick reminder that sometimes it's not that every example will be better with clock replacement. It's just on average, clock replacement is better than FIFO. So I want a new page, and this time I'm not going to add lines. I'm just going to do it like this. So clock replacement algorithm, there's a reason why it's called the clock. It's because instead of thinking of physical memory as a linear sequence, we're going to think about it as a cycle. So each of these little segments, each of these pie slices, pizza slices, each of these is going to be a segment, a frame of memory. So we've got here, we don't need to label them. And then in the inner track, I'm going to keep the use bit. So is this in use or not? Now I'm kind of mapping some page table entries to these because that's what's going to make sense. So I'm going to say A, B, C. I'm going to say that my RAM is full. And it looks like this. So every frame of RAM has something living in it. And here's the use bits in the inside for each of the corresponding page table entries. Okay. Now here's what's going to happen. We're going to have what's known as the victim pointer. And the victim pointer is going to start out here. What we're going to do is we're going to check the use bit. The use bit is 1. Therefore, I know since the last time it was cleared, this was used, which means this was probably used pretty recently. So this is not a good choice to evict. So what I'm going to do is I'm going to set its use bit. Uh-oh. It's acting up again. I'm going to set its use bit to 0. And then I'm going to advance my victim pointer to the next entry. And I check the use bit there, and I see that the use bit is also 1, so it's not a good choice. So I'm going to reset it to keep track of does this get used again. And then I'm going to advance my victim pointer again. I'm going to use a different color. To the next one. And this is going to repeat until we get to this entry here. Now, D. I look at the use bit and I see that it is 0, which means that since the last time we cleared this bit, D was not used, which means D is a great choice to evict. So we will get rid of D. We will insert K. We will not set the use bit. That's the MMU's job. And we will advance the victim pointer. Then what happens is we return from the kernel back to the address translation. This time it's going to succeed, and then we're going to, the MMU will come along, and the MMU will set the use bit here to 1. And we will go around and around and around the clock. Now, some people ask me when it comes to the clock algorithm, what happens if your clock looks like this? So what happens if your use pointers look like this, or your use bits are all ones, that is, everybody was used? Won't you go around in a never-ending loop? And the answer is no, you won't. Because as you check each use bit, you are setting it to 0. Which means that when you come back to the original value, it will be a 0 and you will victimize it. So that is one way to use the use bit to keep track of temporal locality. Oh, excuse me. All right, so that actually marks the end of the virtual memory section of this course. Finally, we are through it. I will try to have the virtual memory quiz up for you later tonight, and then you can get a start on that. So in our next episode, we're going to introduce a new topic, which is scheduling. And some of these same themes of FIFO and LRU are going to actually come back. And then we will, after scheduling, we will be doing devices. So we were coming into the end of the course where all the really, really fun topics live. And for those of you worried about assignments, I can also tell you that as of this point, all the assignments have to do with things up to and including virtual memory. Everything beyond this module, we have no assignments on. You have quizzes on it, but no assignments. All right, so we will see you on Thursday then.
Hello, I'm a Mac. PC, what are you doing?
I gotta get out of here. I upgraded to Vista and now I need new drivers.
Okay.
My printer, my scanner, I gotta search for them.
Okay, go ahead, just calm down. Okay, we'll figure something out. You don't have to keep doing that. It's gonna be okay. Hey, PC!
Weird.